Hi everyone. I'm calling this series of videos. Well, I wish I had watched this video when I started to learn about artificial intelligence. This is part one, which is the basics, and split up into 6 sections. This is section 00. This is the URL in which contains the code that we're going to be going over. When I started to dive into AI back in the fall of 2022, I had a ton of questions that were not easily answered. This video series is the culminations of all the questions that I had about AI. Chances are, when you begin to study AI, you'll run into the same questions that I had. So I'm producing this video and I hope that you'll find it useful. Most of the video is a semi-live demo using Python's Jupyter notebook. The actual Jupyter notebooks that I use are available in this URL here. Okay, so without further ado, let's get started. So I'm going to open up this notebook right here, explain-00 in Jupyter. Okay. So the easiest thing to do is for you is to start with a recent version of Python. I recommend, at least for the fall of 2024, you say start with Python 3.11. I recommend that you install miniconda somewhere. Let me go down to the miniconda. This miniconda is basically a system for having multiple different working environments called virtual environments. And once you create one of these virtual environments using miniconda, you can do this purely in pip also, but it's not optimal. And then what miniconda allows you to do is it allows you to use a specific version for a specific virtual environment, and then you activate it. For the most part, you can follow along with this video using Jupyter, like I'm doing right now, to type in your code and run it. Whenever Python complains of an unknown package, you can get past it by running pip install package name. You might want to do a web search, something like search for the pip install, type in the package name to make sure that you actually have the right package name. All right. Okay, let me show you the PyTorch documentation. Where is it? Here you go. Getting started locally. Okay. For critical things like PyTorch that have a system dependency, like the GPU, for example, I recommend that you use conda to install it, but that's not strictly speaking necessary. As you can see, you can use both conda and pip to install PyTorch. Okay, so this is the URL. I don't know if you can read it, but it's pytorch.org, and the link is right there. Okay, so as of late 2024, AMD GPUs still are not supported directly on Windows, as you can see. If you have AMD GPUs, chances are you're likely stuck using Linux. I'll assume that you have either a Linux or a Windows machine with an NVIDIA GPU installed. If that is not the case, what you'll probably need to do is hunt around the web for some equivalent if you want to follow along with the coding. For explain-00, I think, I'm just going to sort of read it out to you. Unless you have an overriding reason, I do recommend that you use miniconda to manage your virtual environments. And the reason why I say this is because unlike just doing purely in pip, miniconda allows you to have different Python versions for each virtual environment. And I recommend sticking to Python 3.11, even though it's actually not the latest. There's rarely a reason to stick to the latest and greatest. And the reason why is that many of the Python packages for doing things in AI sometimes have surprising dependencies. So you need to be conservative in what you choose to start with. So let's just get started. All right. So once you download conda and install it, here's what you can do. You can use conda create -n for name, the name of the environment, and then you're telling conda to basically start with Python version 3.10. And this will create a new virtual environment called v310, and it'll start with Python 3.10, like you specified. Now, even after you did this, you can still manually create additional virtual envs directly using pip or the Python's, which is the Python's virtual environment manager. But that's strictly speaking not necessary anymore. So what you can do is you can then activate it by saying conda activate v310, and it'll basically change the logo, the prompt to v310. And now you're going to be using it. So you can use pip to install packages afterwards. In general, what you should do is you can use pip to install packages unless it requires conda to install. Technically speaking, PyTorch does not require conda to install. But I generally like to use conda to install it. Unless conda does not handle it, then I use pip. So for example, what you can do is you can conda install PyTorch 2.2.2, and then PyTorch CUDA, this is the driver stuff, starting at 12.1, and then install CUDA toolkit using the channel PyTorch and NVIDIA. This will install a specific version of PyTorch into the current conda environment, which is going to be v310 that you just created right up here. And then when you're done with doing whatever it is that you need to do, you can then say conda deactivate to leave the environment. Oh, and I forgot to say one thing. The $ here is the default Unix shell prompt. So when you're typing this in, do not type in this character. Just type in this portion that I just highlighted. All right. So once you install PyTorch, you can get by, at least for up to part 05 or explain-05, you can do everything that you need to do with the CPU version of PyTorch. But once we get into the actual large language model stuff, that's not going to suffice. But at least for up until explain-05, you can use CPU version if you do not have a GPU. Okay. So now I believe these are the packages that you will need in addition to PyTorch for at least up to explain-05. You'll need NumPy, SymPy, SciPy, Matplotlib. Oops, sorry, Matplotlib, and wait. Matplotlib, GraphViz, and Jupyter. Jupyter is what I'm running right now. And then let's see what else is there. Oh, I guess I need to cover this part. So dot here means a single period. It means that this is a Unix-ism, Unix shell-ism, I should say rather. It means to load the script and execute it in the current running shell. Microsoft, PowerShell, and whatnot have a slightly different way of doing it. So for example, if you just wanted to use pip, you can just create a virtual VMs directory, and then you can say Python 3 module venv, and then give it a name in the VMs directory. And this directory doesn't really matter. Like, you call it whatever you want. Just pick something that you'll remember to use. And then there will be several activate scripts that can be used to modify the running shell's environment, right, in this directory. But you have to make sure to pick the right activate for your shell. And once you do that, your prompt should change to something like this. And remember, don't type in this $. Okay. So let's get started. Let's just jump right in. Okay. Now I'm hitting Shift Return to execute the code in the box. So I'm just doing some setup here. In the next box, I'm defining a quadratic function, f, and its value at x equals 3 is going to be 20. In the AI world, visualization is king. You're going to be dealing with billions of numbers and sometimes hundreds of billions of calculations, maybe even 10 to 100 times that much actually, in the largest AI models. And it's really way too many numbers for humans to work with directly. So that's why we use things like matplotlib and what have you to plot it. Now, okay, I'm going to draw the graph of this function f. Excuse me. If the graph above, let's assume that this graph here is the measured error of something. Then what do you want to do? You should measure the error. Hint, you want to make the error as small as possible. That's just common sense. So if you're on the right side of this graph, you're going to follow the slope towards the left, towards this lowest point right here. If you're on the left side of the graph, you're going to follow the slope towards the right, towards the minimum point right over here. So how do you calculate the slope of any function? And that's what calculus is for. The definition of the derivative, that's what it's called. The slope is, the technical term for the slope is called the derivative. The definition of the derivative is that you evaluate the function in two locations separated by a small delta h. And then you divide by h. And to make it more accurate, you need to make sure that you have to make h as small as close to 0 as possible. But obviously, don't make it 0, otherwise you'll crash your program. So let's do a simple example of calculating the slope of f at x equals 2 at 2/3, x of 2/3, and it should be 0 because that's actually the 0 point. Oh, but wait, oops, sorry, that's f of x at h, and here is the slope at x at 2/3. And why is it not 0? This is a trick. It is 0. Take a look at the exponent here. The exponent is -5, but this means that the slope is 3 times 10 to the power of -5, which is effectively speaking 0. So be careful here. There's there's lots of gotchas like this all over the place. Booby traps are a dime a dozen. Don't be a booby. Pay attention. Now I'm showing you some very basic calculus, which is has some very basic math, using some very awesome ASCII art. This thing is called the derivative, this symbol right here. Okay, it looks like division, but it's sort of division, but it's not really. What this reads is the derivative of x times y with respect to x, right? And that's how you read it. And if you want to be a little bit faster, you can say d of x times y, d of x. This sort of acts like a division, but not 100%. The d of x right here usually means delta, or a small change of. Right? So let me repeat. This entire fraction is read as d of x times y with respect to the d of x. Or simply d of x times y, d of x. Follow along with the algebra, and you'll get y as the result. Simple algebra can be used to simplify the math for x plus y with respect to x, and for multiply and add and subtract, the derivative with respect to the second variable, we did it for x now, meaning the second variable meaning y, is going to be symmetric. D of x plus y dx is 1. D of x plus y dy is still going to be 1. Try to follow along with the laborious derivation of derivatives for x raised to the power of c. So what this first line is doing here is that we're multiplying x plus h by the worked out second order polynomial for x plus h squared. Okay, there's a minus x cubed here, remember, because the original formula is f of x plus h minus f of x, then the entire thing divided by h. So we just simply gather up the like terms, and the x cubed disappear because you have x cubed over here and we have minus x cubed over here, so they cancel out. And then what you do is you pull out the h, and the h in the numerator and the denominator cancel. Oh, this should really read as h squared actually. Apologize, typo. So what the resulting thing that we get is the 3x squared plus 3xh plus h squared, and these two guys become 0. Why? Because h approaches 0. That is the definition of the derivative, or this I guess is actually called a limit formula. Right? As h goes to 0, these two guys become 0. Okay, and h's cancel out, so that's what you're basically left with 3x squared. Now we're going to use SymPy to do symbolic math. Okay. SymPy and SciPy and NumPy are kind of like poor man's version of Wolfram Mathematica, which is an awesome tool to use. But it can cost up to thousands of dollars for anyone who's not in school, so I make do with free software. First, we define 3 symbols. And then we define capital F. And this is the fun thing about Python is that f of x in Python, Python really doesn't know what type x is. It only cares that it has the exponentiation operator. This is the double asterisk right here. That's the exponentiation operator. If it does not, it'll throw an exception when you run it. Let's ask SymPy to differentiate x cubed. And look at that. It comes with 3x squared, which is the right answer. Now, but when you have to work with the numerical side, it doesn't always do things nicely. So sometimes you have to try a lot of different things in order to make things come out nice or pretty. Okay. But SymPy can be useful. Remember that capital F we just defined above? It's smart enough to do symbolic differentiation of it. Let's just try that now. Okay, let's try that. And as you can see, SymPy was able to differentiate capital F, even though it was actually a function and not an equation. So now you're beginning to see the power and flexibility of Python. We're using the same function to do both symbolic and numeric operations. Right? Here's the symbolic, and now we're doing the numeric. Ta-da! Let's do a slightly different calculation here. We have 3 variables, a, b, and c, and d is a times b plus c. Now we are redefining h, and we're redoing the same calculation and generating the slope of a times b plus c with respect to a, and it says it's minus 3. This gives us a powerful hint as to how to do numerical differentiation in a systematic manner. Let's move over to the value class. It is a wrapper for a number, or scalar in other words. And I claim that with just a few lines of code, we can start doing numerical calculus very easily. I didn't invent this, by the way. The calculus was invented thousands of years ago, obviously, or hundreds of years ago, I should say, rather, by some very smart people. And in terms of how calculus actually applied to AI, I really didn't understand it until I saw some videos by a very good gentleman named Andrej Karpathy, and he has a package called Micrograd, which a chunk of my video is actually based on. So kudos and thanks to Andrej Karpathy for that. So let me explain the value class. Self.data is just the number that we track. Prev underscore prev is used to keep track of the expressions, and op is purely for we can print it nicely later. Requires grad is a PyTorch-ism. We're not using it yet, but once we get into using PyTorch, we'll see it. In the initializer, we're just simply assigning the data, the prev, and the op fields. The double underscore add, the double underscore mul, double underscore pow, these guys are Python-isms, and you use them if you want to add numerical capabilities to your classes. And if you want to do that, this is how you do it. ReLU here is just a fancy AI shorthand and it stands for rectified linear unit. fancy, right? All it does is if x is greater than or equal to 0, return x. Otherwise, it returns 0. So, tan is hyperbolic tangent, and it shows up quite a lot in neural networks also. Just take my word for it. The formula for this, again, you'll have to take my word for it, is basically e to the power of 2 to the x, 2 times x minus 1, e to the power of 2x plus 1. That is how you calculate hyperbolic tangent. The neg operator, as you may have guessed, is the negation operator, and notice we're implementing it in terms of multiply. radd stands for reverse add, and it's used to handle situations where x and y in x plus y are not the same class. For example, if one is a value and the other is just a regular number, and the class has an radd operator, Python reverses the arguments and basically calls radd for you. Right? And rmul is basically the same way. Notice that we don't have a div operator. Why? Because Python actually has 2 division operators, true div and floor div. We're not using floor div here. Floor div returns an integer, not a float. Notice that we're implementing true div in terms of multiply and exponentiation by -1. REPR is just for representation. Repr is just for purity for printing purposes. And as you can see, the value class acts almost exactly like a normal Python number class. And here, testcalc is doing the exact same calculation that we saw earlier, a times b plus c, and is calculating the slope of the expression. Okay, so if we give testcalc with 2, -3, and 10, slope is going to be 3, which is what we expect. Now we can send in testcalc with the value to value -3 and value of 10, and you get back pretty much the same thing, which we do. Okay, that ends part 00. Sorry, explain-00 of part 1 of my video series. Okay, see you very soon for section explain-01. Thank you.